We are going to dive into thermodynamics and expand on what we've learned in previous classes with respect to thermochemistry and enthalpy, introduce some new concepts, and talk about overall free energy. So, one of the ideas that has been around for centuries is this idea of perpetual motion, where you have something like an input of water from this tray up here, and then it's returned through this screw, so it's an infinite loop of water. Now, there's myths that I think Da Vinci tried to make one of these. I don't think that's true because there's writings of his that actually say that he thought it was a fool's errand. And it is, because there's no possible way for this to go on in perpetuity, in perpetual motion, because there is some energy is always lost when a mechanical or chemical process occurs. So an example of that is what's called the quote-unquote heat tax that nature has. So if you look at an incandescent bulb, if you have a 100-watt bulb, so what that means is there's 100 watts of electrical energy flowing into it, you get about 95 watts dissipated as heat and 5 watts of light. Now, why do we have these? Well, the whole idea behind an incandescent bulb and how it works is that you have this filament and it gets hot and emits light. And so when you use an incandescent bulb, you are spending most of your energy on heat rather than light. So that's where things like these compact fluorescent lights and LED lights become more efficient. LEDs are actually not lights, they are light emitting diodes. And so it is the flow of electrons that provides the light. There's very little heat, so that's why they are so much more efficient, because very little energy is lost as heat. Another example is, how do you heat your home? My dad does HVAC work, and he says natural gas is so warm. And what he means by that is you're not losing a lot when you're doing natural gas to heat your house. So you burn natural gas, and that heat is that energy is used to pump heat into your home. If you're using electrical energy to heat your home, you have to turn chemical energy, like usually coal, is burned, heats water, which goes into a boiler, which then turns a turbine with steam and sends it to an electricity generator, which then goes onto a power line, which then goes to your house. And so you can imagine that there's heat tax here when you're burning, or there's a heat tax here and 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 here. So this is far less efficient. Now, we don't really want to be burning fossil fuels anyway, so this is not exactly the answer to our energy crisis, but it just kind of goes to show that you can't really beat nature. There is always going to be some sort of energy lost and any type of reaction takes place. So when we're talking about thermodynamics, we're talking usually about spontaneity. So remember that in chemistry, spontaneity means no outside intervention. So it's not like something that just happens quickly or spur of the moment. It happens on its own. So in other words, no additional input of energy. There's no work being done on the system, it just happens. And in class, I had given that example of Snoqualmie Falls. Water naturally flows downhill. That is a spontaneous process. Now, this is not a chemical reaction, this is more like a mechanical thing where you have an object and it naturally floats downhill. Gravity pulls it down. So the goal is to minimize energy. That's usually the goal in mind, and it's not because the object has a goal in mind, but because the forces pull it down. So when we are thinking about how do we minimize energy, that's what we're really thinking about, is we want to imagine that all of the chemicals or all of the pieces are in the lowest energy state possible. So that means that we have minimized the energy. And so in this case, it would be the water has potential energy at the top of the falls and lower potential energy at the bottom. And so the energy has been lowered as it falls down the falls. So this is just a little reminder that spontaneity is not speed. So food will break down spontaneously, but it doesn't happen quickly at room temperature, right? So think about a bag of chips that's been sitting on your counter. If it's not opened, it's going to take a really, really long time to break down. Even if you open it, it will take a really, really, really long time to break down. However, if you eat that chip, you know that it is able to be broken down. So chemically, the energy that of the reactants is higher than the energy of the products for that corn chip, and it will break down spontaneously, just not fast. So we will talk about kinetics this term as well, but just remember that when we say spontaneous, we mean can it happen without an input of energy, not how fast does it happen.